So we shall continue our study with arguments. So an argument is a sequence of statements, and an argument form is a sequence of statement forms. All statements in an argument, except for the final one, are called the premises, the assumptions, or the hypotheses of the argument. The final statement is called the conclusion of the argument. In mathematics, an argument is not a dispute. It is simply a sequence of hypotheses ending in a conclusion. One of the most popular arguments is if Socrates is a man, then Socrates is mortal. Socrates is a man, therefore Socrates is mortal. So that argument has the form if P then Q, P therefore Q. To say that an argument form is valid means that no matter what particular statements are substituted for the statement variables, if the resulting hypotheses are all true, then the conclusion is also true. For an argument to be valid, it must have valid form. So in order for an argument to be valid, the conclusion must necessarily follow from the assumed truth of the hypotheses. Notice that this means that an argument with false hypotheses can still be valid. As an example, if Zeus has 4 legs, then Zeus is a dog. Zeus has 4 legs, therefore Zeus is a dog. So notice that this argument actually has the same form as the example of the Socrates argument. Hence, this is a valid argument, even though this first statement is not necessarily true. So in order to test an argument form for validity, first, we identify the hypotheses of the argument form. We then construct a truth table showing the truth values of all the hypotheses and the conclusion. A row of the truth table in which all the hypotheses are true is called a critical row. So the argument is valid if and only if there are no critical rows with a false conclusion. So we will now determine whether this argument form is valid. So we had 3 statements, 3 statement variables. We have P, Q, and R. So remember, that means we're going to need a total of 8 rows. So let's first look at not R. Let's create a column for not R. Remember, negation just switches truth values. Let's now create a column for Q or not R. So a disjunction is false only when both are false. So row 3, both are false. And row 7, both are false. And it is true everywhere else. Let's now create a column for P and R. So a conjunction is true only when both are true. So row 1, both are true. Row 3, both are true. And false everywhere else. So now, let's go ahead and look at if P, then Q or not R. So remember, a conditional is false only if the hypothesis is true and the conclusion is false. So rows 1 through 4 have a true hypothesis, so let's look. Row 3 has a false conclusion, and that's it. So it's true everywhere else. So by the way, that is our first hypothesis. Our second hypothesis, if Q, then P and R. Same rule, so rows 1 and 2, Q is true, but in row 2, P and R is false. And then rows 5 and 6, Q is true, and P and R is false in both of those. And it is true everywhere else. And that was our second hypothesis. So now we can do the conclusion, if P, then R. Now we actually only care about the critical rows, which are rows in which both hypotheses are true. So row 1, they're both true. Row 4, they're both true. Row 7 and row 8. So those are the only rows I'm concerned with for the conclusion. So the first row, if P then R is true. The fourth row, it is false. And then the 7th and 8th rows, it's true. And now if we look, we have a false conclusion in a critical row. Therefore, the argument is invalid. All it takes is one false conclusion in a critical row for the entire argument to be invalid. So an argument form consisting of two hypotheses and a conclusion is called a syllogism. The first hypothesis is called the major hypothesis, and the second is called the minor hypothesis. So the very first example we looked at, the Socrates argument, is a syllogism. The most famous form of syllogism is Modus Ponens, which is Latin for method of affirming. It has the form if P then Q, P therefore Q. Notice again that this is the exact form of the Socrates argument. And here's a truth table confirming that is valid. The second common type of syllogism is Modus Tollens, Latin for method of denying. It has the form if P then Q, not Q, therefore not P. And again, here's a truth table showing that this is valid. A rule of inference is a form of argument that is valid. The following several slides will give common rules of inference that we will be using throughout our study when we start looking at proofs. Notice also that since both Modus Ponens and Modus Tollens were valid argument forms, they are also rules of inference. So we have generalization, P, therefore P or Q. We also have Q, therefore P or Q. Next we have specialization, P and Q, therefore P. We also have P and Q, therefore Q. Conjunction, P, Q, therefore P and Q. Elimination, P or Q, not Q, therefore P. We also have P or Q, not P, therefore Q. Next, transitivity, if P then Q, if Q then R, therefore if P then R. Next, we have division into cases, P or Q, if P then R, if Q then R, therefore R. And finally, we have the contradiction rule. If not P, then a contradiction, therefore P. What this says is if you can show that the supposition that statement P is false leads logically to a contradiction, then you can conclude that P is true. So a very common logical puzzle is known as the island of knights and knaves. So the logician Raymond Smullyan describes an island containing two types of people, knights who always tell the truth and knaves who always lie. You visit the island and are approached by two natives who speak as follows. A says B is a knight. B says A and I are of opposite type. We wish to determine what A and B are. Well, let's suppose that A is a knight. Well, if A is a knight, then A is telling the truth. Well, this means that B is a knight, which would mean that B is also telling the truth, which implies that A and B are opposite type. But this is a contradiction, because A and B, we assumed A is a knight, which means B is a knight. They're the same type. Therefore, A cannot be a knight. And since there are only two types of people, that means that A is a knave. So A lies. This means that B is not a knight. Again, since there are only two types, this means that B is a knave. And just to verify, that means that A and B are not of opposite type, so they're the same type, which is true. So A and B are both knaves. Except let's look at another example. So we're about to leave for class in the morning and discover that we don't have our glasses. We know the following statements are true. If we were reading our class notes in the kitchen, then our glasses are on the kitchen table. If our glasses are on the kitchen table, then we saw them at breakfast. We did not see our glasses at breakfast. We were reading our class in the living room, or we were reading our class notes in the kitchen. And finally, if we were reading our class notes in the living room, then our glasses are on the coffee table. Where are the glasses? So to make this simpler, let's define some statement variables. So we will let RK represent reading in kitchen. We will let GK represent glasses are on the kitchen table. We will let SB represent saw glasses at breakfast. We will let RL denote we were reading in the living room. And we will let GC denote the glasses are on the coffee table. So the first statement said that if we were reading the class notes in the kitchen, then the glasses are on the kitchen table. Right, that was this one. The second statement says, if the glasses are on the kitchen table, then we saw them at breakfast. Right, that's that statement. Oops, wrong one. That's that statement. So we can conclude by transitivity, if we were reading in the kitchen, then we saw the glasses at breakfast. So there's our first argument. So we now know that if we were reading in the kitchen, we saw the glasses at breakfast. The third statement says that we did not see the glasses at breakfast. So we have not SB. That now takes care of statement 3. Therefore, by Modus Ponens, we can conclude we were not reading in the kitchen. The fourth statement said we were reading notes in the kitchen, or we were reading notes in the living room. So that was this statement. But we just showed that we were not reading in the kitchen. Therefore, by elimination, we must have been reading in the living room. Then the final statement said if we were reading in the living room, then the glasses are on the coffee table. And we just showed that we had to be reading in the living room. Therefore, by Modus Ponens, the glasses are on the coffee table. So the glasses are on the coffee. So a fallacy is an error in reasoning that results in an invalid argument. 3 common fallacies are using ambiguous premises and treating them as though they are unambiguous. Circular reasoning, that is, assuming what is to be proved true without having derived it from the premises. And lastly, jumping to a conclusion without adequate grounds. Two common fallacies that students make. First is the converse error, which is if P then Q, Q therefore P. Right? Remember that a conditional can have a true conclusion but a false hypothesis. The second is the inverse error. If P then Q, not P, therefore not Q. This is a fallacy for the exact same reasoning as the converse error. A conditional statement with a false hypothesis can still have a true conclusion. Lastly, an argument is called sound if and only if it is valid and all of its premises are true. An argument that is not sound is called unsound. Right, so remember that an argument can be valid but have a false premise or more than one false premise. However, if it's valid and all of its premises are true, then we can say that it is a sound argument. So this concludes our study of arguments.